you, everyone. Apologize for the delay. We have a long queue in the registration. So, good morning. My name is Francisco Benita. I'm lecturer in Singapore University of Technology and Design, SUTD. Very happy to be here and share some of the research we are doing in Singapore with colleagues from different departments, engineering, computer science, architecture. It's really a multidisciplinary project with a lot of Python involved, coding, particularly GeoPython. So today we're going to discuss how to compute walkability indicators at the city level. Walkability is a very important topic. Actually, in the morning when I walk here, 15 minutes walk, very comfortable, very convenient, safe, clean, organized, signs everywhere, so easy to walk. Yesterday also, when I went to the city center, it's very walkable here. In Singapore also, there is a huge initiative how to make the city more walkable, bikeable, because that brings a lot of positive aspects in the city. So let's just start with the introduction. So welcome to the workshop. So having a way to assess walkability is very important for city planners. Here we can see some photos of Philippines in Manila. So there are some areas that are easy to walk, easy to explore. Some other areas are not. If you have the opportunity to experience traveling in Thailand or Indonesia, some parts are quite challenging, right, to walk there, so it's not so easy. So there is all this initiative to encourage city planner to improve the walkability of these areas. So it's important having a way to assess walkability because it brings a lot of positive aspects, such as you can ensure that the residents can reach a variety of amenities within a walking distance. There are some health benefits. It also fosters social interactions and a lot of many positive things. Now, today we are going to explore how to quickly compute walkability using a data-driven approach. So gathering data from different sources, processing the data, and computing some walkability metrics to assess the quality of the urban space. So we're going to use some libraries, GeoPandas, OpenStreetMap, networks, Matplotlib to create some data visualizations. So please go to this website to download the materials. So this link will send you to the PDF file here. You can take also a photo to have the URL there. And we have also a website where we are actually posting all this information, some tutorials, some tips. And the interesting thing of this project is that the focus is in Southeast Asia. So Singapore has a lot of partnerships with Southeast Asian countries. And also particularly this project is based with students. So we have university students, very young, since year 1, year 2, all the way to final year, working on this website, and actually are the students who are creating the website, creating the script. So we give them some basic training, and then they are very creative, and they go and compute a lot of things. So I can just quickly show you the website. So this is the website. Again, this website was created by the student. Maybe it's not so very appealing, but it's fun. I'm working with students, with young students, very enthusiastic. So here you can see some names of the students actually involved in the project. You have the description of what we do here, some of the libraries we utilize to process data, to process geo data frames, to create plots, to do some network analysis, to do spatial queries. And if you go to the menu datasets in the left, you can see that for some cities, we actually have some data available because gathering the data is also it's not a trivial task. You need to go and call some APIs to retrieve the data that you need. So it's not so difficult, but it's not so trivial. So, and why we Can you hear me in the back? Alright, so why we focus on this is because we have another department, the social science department. They actually collect single data from GCP, about 1,000 components in GCP. And the survey has social demographics, but also has opinions about different aspects of how perceptions about safety, about transportation, mobility, urban governance. And the idea is we would like to compare objective data, computing with a data-driven approach, quantifying walkability, and then also compare against subjective data, perception of perspective. But maybe it's very interesting because in the Western approach, the way you compute walkability, connectivity, all these things, in Southeast Asia, some regions, it doesn't really apply. Because even if you provide all these features, the people have other reasons for not working. Because, for example, in Indonesia, working is a similar level status, showing that they are poor. So even if they have a very nice area to work, people will not work. And you cannot capture this data. You need to the data to quantify. This is why we focus on this particular section and explain in the language diagram. Now I will ask you to go to this link here in the Google Colab, in the code. You click there. There is a notebook code. So today we will go to this Colab notebook to explain the different sections and explain how are we doing on this So again, maybe try So there are a lot of ways to access portability, a lot of methods, particularly when you talk to data, the open data. So some of them are related to connectivity, that we use during the pedestrian network, in order to graph, remember the connectivity, the edges, the nodes, how many are there. Also, population density is very important because highly populated areas are more likely to have more amenities, more definitions. So also the current relation is important because it has lots in the Because I okay. Maybe can I lower down the volume a bit? Yeah, this one. Okay, maybe. Thank you. Okay, so maybe we'll try to be careful with the mic. So great to hear that many of you have already experience with OpenStreetMap. It's a great source, open source data. You need maybe an API key. Sometimes you don't need the API. And you can gather a lot of information with respect to amenities, the street network, the land use also you can have. Now, some of the issues with OpenStreetMap, particularly in Southeast Asia, that is not very accurate. So we have been working with colleagues from Ho Chi Minh, and they told us that the street network from OpenStreetMap is not really, it's like I don't know if it's all or not. Yeah, it's not updated, but also it's not really accurate. So they told us that what they do in these cities, they focus on a specific region and they build their own data, basically. So for some cities, actually, it's not very accurate. From Switzerland and some European cities, I believe it's fine. In Singapore also is fine. But in some other cities, it has limitations. Population count, this is from WorldPop. This is also open data. And what they do is they collect satellite images, and then they produce raster files or pixel data. And then for every pixel, you can see an approximation of how many people live in each pixel. And those pixels could be 1 kilometer by 1 kilometer, 100 meters by 100 meters, different granularity. The next one is building footprints from Microsoft Buildings as well as OpenStreetMap. But actually, Microsoft Building Footprints is more updated, so it contains many more buildings, so it's more accurate. And what they do is they create a lot of polygons. And when you download the data for Basel, for example, you will have hundreds of thousands of rows, where each row is one building, basically. So one row in the data could be this university, the Northwestern University. And then we will explore also elevation data, just to do a very simple calculation of the terrain, to see if there are slopes or not. So those are the data sets we will be using today. But there are actually many more. You can use also web scraping, for example, to collect data from Google, to extract amenities from Google, or to extract reviews also from Google. So there are many ways to gather all this. So we will start at the city level analysis. And the Colab notebook, the example is for Jakarta. Okay, so now we are going to switch to Colab. Go to this website that I mentioned just now. In the menu datasets, Google Colab code. The script is there. Or also you can click here. So you click there, it will send you directly to the Colab we will be using today. Now let me just show you. This is the notebook. Are you in the notebook there? Ready? Okay, great. So the first thing to do is we need to create a copy of this. So you can actually modify the code and run by yourself. So we're going to menu File, Save Copy in Drive. To save a copy of the script in your Google Drive. This is the first thing you need to do. Now, I will be not doing this because it's time consuming. So I will be showing you just the outputs, but you can actually run the code. Some parts of the code may take time, particularly when you are going to read heavy files. It may take some minutes, but it's working. I just tested yesterday, so it will be fine. So the code contains what we talk now about data sources, about some indicators we are going to compute, the walkability, and later we are going to talk about isochrones or catchment areas or service areas. So we can actually do that for multiple cities. This notebook in particularly is for Jakarta. Have you been in Jakarta? In Indonesia? Bali? No? Go, it's very nice, Bali. So, all right. So the first line here, this is used to install the package to download files from Google, from Google Drive. So what we're going to do is we're going to download files from open data sources. And then we're going to push this file in your Google Drive, because later you would like to read it from there. Now, there is a reason why we do that in that way, and why we don't read it from other cloud services. Because you can actually read the files from Dropbox or from other cloud services, but then it's very slow. Particularly if you work with Colab, if you use the Google settings, everything is faster. So that's the business model for them. So that's why we are going to push the data in Drive, because it's faster to do the calculation. And this library is going to do exactly this. Okay. Next, we are going to define the environment. So the packages we are going to use. Very standard packages. We are not using anything sophisticated. Also, we are not creating a library in particular. So we are going to use the one to extract OpenStreetMap data, to manipulate GeoPandas data frames, geodata frames, to do calculations with lat long data, and to do some network analysis with networks. And this one is to do spatial queries. So we do the setting of the environment by running this chunk of code. It will not take so much. And then we're going to import the packages we need. So we're going to import all the libraries we installed. So OpenStreetMaps, ALOS, Matplotlib to do some basic visualizations, GeoPandas to manipulate the geodata frames, networks to analyze this is to analyze the pedestrian network as a graph. Now the next two portion of the code, what they will do is they will create a folder in your Google Drive. In your Drive, it will create a folder called Walkability project, and in that folder, it's going to push the outputs. Okay, because later when you need to read again the file, you don't want to read it from the cloud, because you don't want to download the data again. You just want to read it locally. So this is the way to do that. Create folder on your Google Drive and read from there. Okay, the first thing to do is from OpenStreetMaps, there is a file called boundary file, and this contains different boundary regions for the cities. This in particularly is the boundary of Jakarta, and you can see that there are many islands over here, because Jakarta contains by right all these many islands. So this is the boundary of Jakarta, the whole city. And for that boundary, we would like to actually extract multiple data sources. We would like to extract the street network, the pedestrian street network. We would like to extract the population counts, how many people live there per 100 meters, square meters. We would like to extract the buildings, and we would like to extract the elevation, changes in elevation. So the way it's coded in Notebook is we create functions. Every function is going to do one step in particular. So this function here, we are going to pass the URL file where the boundary data is, in this case for Jakarta. And then it's going to read the file using GeoPandas, and then create a plot to visualize. Make sure that we are reading the correct file. Now this file is in GeoPackage format. GeoPackage is a GPK. This is wrong. It's GPKG. So it's different format. Also, you can read shape files or GeoJSON files. So this is the boundary data. Now, this is also a very standard process where you download the pedestrian street network for your boundary using the OpenStreetMap library. So here we create another function And in this function, we are going to pass a geodata frame that contains your boundary file. In this case, the boundary of Jakarta. This is the argument to pass. And then for that boundary, we are going to read the first row, which contains the geometry of your city or your area of interest. And for that geometry, you are going to extract the graph. And the function to call here in the library is graph from polygon. So you would like to extract the graph from the polygon that you are passing. And the network type, we are going to set this to walk because it's the pedestrian network that we are interested in. Okay? This is important because if you don't set this network type, I think by default it returns the driving network for cars. They are different. The pedestrian and the driving network are different. And then we pass the simplify argument equal to true because what this argument is going to do is it's going to remove nodes in the network that you don't need it for the analysis. So it's nodes that are there, but only for creating curvatures or things like that. So you actually don't need these nodes. I want to simplify the graph for you. And finally, we plot. So now this particularly line of code, it will take few minutes because you will extract a huge graph because Jakarta is huge. I believe if you are running, it's still running. It will take maybe 5 minutes. So that's why I don't want to run it myself here because it will take a while. So we are actually in this portion. Okay. So this is the function to extract the pedestrian network. And again, comments from our colleagues from Ho Chi Minh in Vietnam, they told us that the pedestrian network for Vietnam, Ho Chi Minh, is not really accurate. Like it is missing a lot of areas and things like that. All right, then we have some functions here that they are going to allow you to explore the graph itself. So you would like to see how many, you would like to explore how many nodes are there, how many edges are there. Every edge is a road. Every node is going to be an intersection in the city or dead ends node. So in this particular case, we have around 180,000 nodes and around 500,000 road segments, or pedestrian road segments. That's why it's taking a lot of time because you are going to load 500,000 segments of road. So it's a bit large. So this is just to understand a bit more about the graph itself. Okay, I will stop here maybe just a few minutes walking around to make sure that everyone is here.
Sue, hey.
Okay, hello, hi. Much better. Okay, thank you. Yes, understand. Okay, I think this is much better. Thank you very much for that. Thank you. Yeah, actually, we are going to stress the Wi-Fi of the unit. So we are going to test how fast is the internet, because everyone is downloading the same data. And I believe in the other workshop also they are doing some calculations. All right, so let's continue. So I think everyone is here, where you can actually explore the properties of your pedestrian network. And the next thing to do is do some basic calculations about the network length. This is just going to be the sum of the length of your pedestrian network. And here we have a for loop. We define, again, a new function where for every edge or every node U and B in the graph, you are going to sum the length there. Now, the length is in meters, but because it's huge, we're talking about the whole city, we're going to divide by 1,000. So then the total length is going to be in kilometers, the total length. Okay. And then this code here, before computing the length, also you have a way to showcase the attributes in the network. So when you print the geodata frame associated to the edges, for example, you can see interesting metadata. So for every row, which every row is one edge or one segment of the road, you can have information, for example, about the name. You can have the name of the street in some cases. You can have the length. And actually, this length is the one that we are summing in the next function. So what we are doing is, or another way to see that is sum all the values in the column length. This is one way to do that. Okay. So this is the metadata associated to the network. We can also convert the graph, the network, into geodata frames to do some manipulation, because if they are the geodata frames, you can do summary statistics, things like that. Easy to do analysis. Okay, so we were talking about this portion of the code where you compute the total length. So in Jakarta, I think this number may change because OpenStreetMaps keep updating the data. So so this number may be different because they keep adding road segments. Now, the stringlet itself is not very meaningful, but the street density is meaningful. So what we need to do is we need to divide the total length of pedestrian network in the city per square kilometer. That is meaningful because then we can compare this with other cities. And what we do is, again, another function where we use the total length we compute before. In this case, about 27 kilometers of pedestrian network. And we divide by the total area of your boundary data, or the region of interest. So the total area of your city or your area of interest is given in that line. So you actually extract the area in meters, I believe. Everything is in meters. And then you just compute the ratio. And then here you have that in Jakarta, the boundary is about 665 square kilometers, 665 square kilometers. This is the size of the city of Jakarta, which is more or less accurate. If you go on Google area of Jakarta city, you will get a number like this. And then when you take into account these 27,000 kilometers of road network, you will see that on average you have about 40 kilometers of pedestrian network per square kilometer. Now, how good or how bad this number is, this is relative. So we need to compare this with other cities to actually tell if it's good or if it's little or huge. Okay, so the number itself is not meaningful after we compare with another city. And this is why we have multiple cities, because we would like to compare across cities. Right, I'm going to the slides here. Then we talk about the row density. This is what we discussed just now. This other metric is also useful because it helps you to understand the intersection density. And the intersection density is just counting how many nodes are junctions. Junctions meaning degree 2 or more. So degree 2 is a node that is connected to at least 2 nodes. If you're walking and then you see an intersection, you can go 2 ways, right? You can explore 2 ways. So that node is degree 2. Or if you can explore 3 ways, then it's degree 3. So this is also important because it helps you to understand the connectivity in the network, the degree of the node. So this function is going to do that. It's going to count how many nodes are junctions. In this case, we count, and then we divide by the total area of the city in this line over here. And we say that the intersection density of my city is about 201 junctions per square kilometer. How good, how bad this number is, we need to compare with other cities. All right, this is everything about the road network, simple calculations. And then we can talk also about the population count. Here, very quickly, let me show you in QGIS how the data is retrieved. So here you have Basel, Switzerland, and the data is for the whole Switzerland, and then the input data is a raster file, it's a pixel data. And then for every pixel, you can see here in the band, for example, 61.42. So around this region, you have 61 people per square kilometer, per 100 meters per 100 meters. So the resolution here is 100 meters by 100 meters. What we need to do is, because it's pixel data, we need to vectorize this. We need to convert this as a vector data. I think the layer here is not working. But you can do it in QGIS or in Python, how to vectorize this. And then once it's vectorized, you can process the data as a geodata frame. This is what we do. So in this repository, the population count is already vectorized. Okay, the input data was pixel data we process, and then the output is geodata frame. Okay, population counts. Okay, so this is what we have in here. So we read from the URL the GeoJSON file, and then we explore the data frame, and then we will have all these many columns, but the column that we are interested is the column DN, because the column DN contains the total people per pixel or per polygon. So in this case, this row represents one grid cell of 100 meters by 100 meters. We have the coordinates here here we have the coordinates. And in that specific area, there are 139 people, 139. So you go and compute summary statistics from geodata frame, and on average, you have 150 people per 100 meters by 100 meters. 150 people in 100 meters by 100 meters. So actually, Jakarta is one of the highest densely populated cities in the world. Then you go and plot the data to take a look, and you will see that population count ranges between 0, which is dark blue, all the way to 220 people in yellow color. And actually in Jakarta, in the west, is where most of the people live, in the west side. You can actually zoom in, focusing the coordinates you are interested. For other regions, of course, you need to play with the limits. You need to set the limits to the area of interest you would like to visualize. So the population data looks like this. Now, how can we use it to quantify a metric of walkability? It will come later. Just for now, just stay with me with this part, how to read the data. Later, we are going to do some analysis. Now, the next one is extracting the building counts. This also may take some time to run because we are going to extract all the buildings for Jakarta that contains, I think, more than 1 million of objects. So it's a very large file. And then actually here is when it starts to become interesting, because if you are doing for multiple cities, then you need to store these objects in RAM. And then sometimes you can have exceptions, issues, that you cannot store the data. And then you need to refine the code in a way that you remove the object that you don't need, because here is when the big data actually starts to appear. And this is also the reason why we do from Google Drive, because if we read the data from Dropbox or any other source, it's very, very slow in Colab. But if you do that from your drive, it's much faster. So this is a sample of the output. So you can see here all the buildings in the city. Every row is one building. You also have metadata such as name. Well, for some of them, there is no name. Some others, you may have metadata. The last data set to explore today is elevation data to see if there are slopes in some regions. And this one is simple contour lines, okay? So in this function, we are going to, again, read or pass as an argument the GPKG file that contains the contour lines. And let's just plot this. So the plot looks like this. So the elevation range in Jakarta goes to -10. There are actually some regions below the sea level, all the way to 140 meters. So there are not very high regions. And actually, Jakarta is facing issues of flooding. Many areas of the city are flooding. All right, so this is just the data sources. We haven't discussed much about how we compute walkability, but this is just coming now here in the isochrone level analysis. So far what we did is we download data at the city level and then get ready to start to compute walkability for some regions of interest. So what we are going to do is we're going to compute isochrones or catchment areas or service areas. And for that particular region of interest, we're going to compute walkability metrics. And then when you do this for multiple isochrones, then you can start to discover insights. So which regions of the city are more walkable than others. So the idea is to choose a point of interest. And then for that point of interest, extract a subgraph where the subgraph is going to contain all the regions you can explore within some distance, within 600 meters or within 800 meters. And this will represent probably a 10 minutes walk or 15 minutes walk. So in the code, we're going to compute all these metrics at the isochrone level, and we're going to compute 5 of them. Intersection density, actually we do that, we already did this at the city level, but now it's just to repeat this for the isochrone. Network density, again, we already compute this for the city, let's just do that for the isochrone. The population density is the same. How many people live inside the isochrone of interest? The building density is the proportion of buildings or the proportion of area covered by buildings in your catchment area. And the elevation, this is just very simple, it's just the range, the difference between the maximum and minimum elevation in the isochrone. And then it's going to give you an idea of changes in slope. So for that, here, we are going to read locally the pedestrian network. This is why we connect this to Google Drive. because if early you delete the pedestrian network, you don't want to query again this data. You want to read it from your directory. So, and this is what we are doing here. We're going to read the network from your directory, right? And then for that network, we are going to compute the isochrone. So let me just show you the example of the isochrone. So what we do is we pass a point of interest, lat long. And for this point, it could be a bus stop, a metro station, or the university access point. And for that point of interest, you go and extract a subgraph to understand how many regions you can explore within some walking distance. And the second step, after you have the subgraph, you need to compute a hole, either a convex hole or a concave hole, to actually have a polygon there. Because for this polygon, inside that polygon is where we're going to compute how many people live there, the building density, the intersection density. So in this case, we are using a convex hole, but this is an overestimation of the area. Actually, you can improve this using a concave hole. And this is what we do in this function here. So here, we are going to extract all the nodes that you can visit within some distance. And then for the nodes there, you compute the convex hole, like the envelope that is going to cover all these nodes. So the plot of the subgraph may look like this. You can reach all these nodes and all these edges within some distance. And then you compute here the convex hole, and then you plot. Now for this particularly region, let's compute walkability indicator. So this portion of the code, what it's doing is just plotting in the whole Jakarta where the region is. It's in the west, where we mentioned that it's highly populated. So it's around here. I think it's 500 meters. But you can actually play with the distance there in the code. And now we're going to compute the walkability indicators finally. So finally, in the last 10 minutes of the workshop. So, and then it's just basically repeating what we did at the city level, repeating the same steps. So what we are going to do is, for this catchment area, we need to compute the area inside this catchment in square kilometers, and then we need to compute the total length of the network in that area. And then you have the road density. It's the same idea. And for the intersection density, it's the same. You need to extract how many nodes are of degree 2 inside the service area. And then it's a ratio between total number of nodes of degree 2 or greater divided by the area of your catchment area. And this is what we have in here. Okay? And also, this is why we code as a functions before, because we're reusing the same functions. This function will also work for the whole city. It's just reusing the code. That's why coding in functions is sometimes easier, right? Same here. We okay, so for instance, in this isochrone, there are 60 nodes that are junctions. And the size of, and the total length of pedestrian network is 86 kilometers. Oh, it's large, it's huge. 86 kilometers in this buffer. 86 kilometers per square kilometer. Yeah, 86 kilometers per square kilometer. All right, and then the next indicator is the population density. This one, what we are going to do is we are going to read the population count, we're going to compute overlap. It's actually is the overlap function. Okay. Is this function, is the overlay function. So this function, what it's going to do is going to compute an overlap between two polygons. It's going to give you the intersection of two polygons. And what we want to compute is, for that intersection, the intersection between my isochrone and the total population in Jakarta. And then the intersection is going to be the people living inside my isochrone. And then what I need to take a look is, I need to sum all the values inside the isochrone. So for this particularly example, here you can visualize the total people, okay, in the region of interest. And you need to sum, here for every square, you need to sum how many people is living in every square there. And divide by the total area of the isochrone. And in this example, there are about 10,000 people living in this isochrone. And the total area is 0.69 square kilometers, less than 1 square kilometer. Therefore, the population density is about 15,000 people per square kilometer. Again, it's just reusing the functions we computed before. And the building density is similar. It's an overlap between all the buildings lying inside your catchment area. And then for every building, you need to compute the area. So basically what you need to compute here is the proportion of purple area inside the isochrone. The proportion. So the total area is 1, or the total area of interest will be 1. So which proportion is covered by buildings? And then here we find that it's about 0.4, or about 40% of the isochrone is covered by buildings. This is what we do in this part over here. For elevation change, we see the contour lines. Every line here is telling you the elevation in some region. So some lines may be above the sea level, some others below. And what we do is we compute the range. So we do an intersection between how many lines are inside the isochrone. And for those lines, you compute the difference between the maximum and minimum level. So in this particularly example, this function will compute this difference. So you take the maximum elevation, and you take the minimum elevation, and then you check the difference. So for this particular example, it's 0. So that means it's flat. In this region, it's flat. So it's easy to walk around. There are no slopes. So let's use the last minutes of the workshop for you to play around. And let me just show you some of the possible outputs, because so far we did it for one isochrone, maybe not very interesting. But when you start to compute it for the whole city, it starts to become more interesting. So here, this is Manila in the Philippines. And then you compute a grid cell of 100 meters by 100 meters. And for every centroid, you compute the isochrone. And then you start to divide the city into small parts. And then for every small part, you would like to compute the walkability, right? How easy it is to walk in every small part of the city. This one is for Phnom Penh in Cambodia. This is 200 meters by 200 meters. The whole city was divided in small areas. And then for every 100 meters by 100 meters, we compute the isochrone. And then for that isochrone, we compute the walkability metrics. And then we go back and we map the results at the grid cell level. So the students, what they did here is they did a simple k-means analysis to identify clusters. So for instance, the cluster 4 here may have some properties, maybe some high values of sub-indicators. and they are like spread around the city. This is also interesting. This is for Jakarta. This is using 100 meters by 100 meters. You divide the whole city into very small parts, and for every small part, you compute the indicators, right? And then here we use self-organizing maps based on neural networks to identify similar regions. So for instance, here in the south, this region in green color, they represent a cluster of areas of the city that share similarities. For example, high elevation or no people living there. And why we did this way is because we also have survey data. If you recall early, I mentioned that we have survey data. And what we do is we compare objectively how the walkability is computed with data versus how people feel the neighborhood, if it's walkable or not. And then we compare versus survey data. This is something also we were working. So these are the kind of things you can actually do, right? These have to become more interesting. So yeah, I think that will be the workshop. We can use the last minutes for your questions, comments, suggestions actually to improve this website and the notebook. So I will pass this to students. And again, this is work by students, university students. And yeah. So, but thank you very much for attending the workshop. Yes. Yes. So actually, the building data. If I'm going to the slides, here. I think in the notebook, the building data we're using is from OpenStreetMaps, but the one that is more accurate is from Microsoft. So I think the script is for OpenStreetMaps, and this is again back to the comment that our colleagues in Ho Chi Minh City tell us that OpenStreetMaps is not very accurate. So it's happening exactly this, that there are regions that they are not updated. So the workaround will be try to use Microsoft building footprints because it's more accurate. But the script is not doing that. But it's just a small change. But that's the reason. That's the reason why some areas are blank. Thank you for the question. Any comments? Yes. So we have actually, okay, this is just like an educational module we have for students to learn all these concepts about working with geospatial data. But the research we do with this has different areas. So we do, for example, research related to parks, how easy it is to have accessibility to parks, livability also, how to measure livability in cities, and also comparatives to this. So when we work with the colleagues from social sciences, they are interested in comparing cities. So they would like to compare cities in Southeast Asia. And also we are trying to move, we have some research about cars. We connect to cameras in Singapore, and we quantify the traffic from cameras. So we have like different areas. Yes, one of them is livability. We work with people from architecture, for example. They have all this urban planning agenda. So this is how this project was originally. Actually, we work with ETH Zurich in Singapore. It's called Future Cities Lab. They have a laboratory, and we work with them. They are in the National University of Singapore, but we do collaborations with ETH Zurich in the US. Ah, yes, actually, what we do, I'm just back to the photo here. For some areas where we have survey data, we also collect more granular data because in Southeast Asia, actually the things that bother to people is, for example, street vendors. You have a lot of people vending on the street. You cannot walk some areas. And this cannot be captured with open data. And also this, how easy it is to cross some crossings. And what we have is, for some regions where we have the survey, they also collect this other type of data. But this is something is very hard to collect even from street views, Google Street Views, it's hard to get because some areas of the city are not covered. In Southeast Asia, I think from Europe it should be fine, but I think in Southeast Asia, but yeah, this is a very good, very good comment. So what they do is they have in Singapore we do that with sensors. Actually, you put a sensor and you count how many people is passing. But we have actually for Phnom Penh. In Phnom Penh we outsource the work to have people that go there and then manually count. They are manually counting how many people is passing by or how long it takes to change the signs on a traffic light. They manually collect it. How we do that. Yeah. Comments, questions, feedback? Yes. No, we have what we did is to read the files in Google Drive. But yeah, I think there are ways more efficient to do the queries. So we haven't actually explored that part. Also, feedback from students is when they try to retrieve amenities for the whole city, for example, how many restaurants are in Jakarta, then they cannot do that because they have an exception. But actually, OpenStreetMap limit the query. It don't allow you to extract all this. It's too huge. So this is also why we have this model to actually teach the difficulties of the challenges to doing this for students. Yeah, I will be giving a talk tomorrow about this, but it's more about the educational aspect. Why is this important in Singapore? How we actually teach things to students. So we are very happy, even from high school students. We have a team from high school, and they actually, this is the output from the high school students. It's 3 students from high school, and they actually do this. So yeah, they're very motivated students doing all this. So we're happy with the output from the